Welcome to a new episode of our Ocean Networks Canada series, Surfacing Secrets, Explore the Ocean, Know the Planet. Today we're heading deep into the Pacific Ocean, a place called Endeavour.
Endeavour is one of the greatest places on the planet.
Endeavour is a hydrothermal vent field along the mid-ocean ridge, where heat, chemistry, and life come together in complete darkness.
These are the most active volcanoes on the planet, even though we don't see them because they're covered by the ocean. So it's an incredible place to study.
Endeavour's only discovered in 1984.
But Endeavour is also one of the few places in the world where the deep ocean is not just visited. It is watched continuously, in real time, thanks to a cable observatory operated by Ocean Networks Canada. In this episode, we tell the story behind that choice, why keeping our eyes on one place over time is changing how we understand the ocean. You'll hear from Lawrence Coogan, professor at the University of Victoria, and Steve Mihaly, oceanographer at Ocean Networks Canada.
It's a big iron reactor down there.
This is Eyes on Endeavour. We talk a lot about space, about Mars, about the moon. But right beneath our ships, beneath our feet, there's another world. Dark, active, and still largely unknown. This episode begins in one of those places. Lawrence Coogan is a professor at the University of Victoria and a geochemist who studies how the Earth works beneath the ocean.
Yeah, I'm Lawrence Coogan. I'm a professor in the School of Earth and Ocean Sciences at UVic, and I've spent my career working on various aspects of mid-ocean ridges. So Endeavour's a mid-ocean ridge, so around the bottom of the world's oceans, there's like 65,000 kilometers of mid-ocean ridges, which are submarine volcanoes. And Endeavour's one of these in the Northeast Pacific. When new ocean crust is continually created, where seawater circulates down into that ocean crust and gets heated to 400 or 500 degrees Celsius before venting black smokers on the seafloor.
Steve Mihaly is a senior staff scientist at Ocean Networks Canada, and part of his work is focused directly on Endeavour.
Steve Mihaly, basically senior staff scientist at Ocean Networks Canada. My responsibilities are for Endeavour, or the work that we do at Endeavour.
So when Steve talks about Endeavour, he's not describing a distant research site. He's talking about where he works, a place where the planet is still under construction.
Basically, it's just the sheer magnitude. There's an incredible amount. There's 5 major vent fields there.
So yeah, it's the perfect place.
We've studied such a small fraction of the seafloor. We don't actually know what most of the mid-ocean ridge network looks like. So there's very few places we've studied in anything like as much detail as Endeavour.
But what does it take to become an expert of a place like this? Not just to visit it, not just to pass through, but to understand it in the dark, 2 kilometers down, where nothing stays still. There's no single path that gets you there. And that's where their stories begin. For Lawrence, it started outside.
I guess as a kid, I enjoyed science. I enjoyed anything to do with the outdoors, the natural world. I was always fascinated by that. And yeah, just the other side was I enjoyed getting out hiking in the hills. And so when it came time to go to university, I'd had a great teacher at school who had really taught geology, which wasn't normally offered in schools, but she was so interested in it, she taught it as kind of an extra subject for a bunch of us who were interested. And she really, I think everyone from that class, that was what they wanted to do after it. So I ended up going to university to do geology. Basically, if you could do science and walk in the hills at the same time, that was great by me. So that was my undergrad, and then I enjoyed it and went off to grad school. Basically, I was interested in anything to do with volcanoes, how volcanoes worked, what caused them, how they impacted the environment around them. So I ended up getting into grad school to work on mid-ocean ridge volcanoes.
Steve took a longer way around.
Well, I guess my first sort of thought about becoming an oceanographer occurred when I was actually in grade 9. and I went to the Bedford Institute of Oceanography. So I sort of had that in back of my head nicely like that. And then I didn't go to university right away. I took a year off and went into engineering. So then I did engineering, and university actually worked nicely for me. I did well in school, better than I did in high school. Then I took another large break because after doing graduate work in engineering, and I went away and did music for a while, for about 8 years. So when I came back, I thought, okay, well, the engineering thing, it's not that it didn't work out. It's just that there's so much more when engineering is very focused to very practical, obviously. And it was really nice to know more about the earth itself, in the natural world. So I thought the easiest way to move from a physics kind of background would be into oceanography through, physical oceanography. So I went back to university and I did my graduate work. I got a PhD from UBC, and I worked for a while with DFO in the coastal area mostly, and also, but my graduate work was actually in the currents around Endeavour.
Different paths, different disciplines, and eventually the same place. So this isn't a story about a random spot on the seafloor. It's a story about one of the rare places where we decided to stop passing through and start paying attention. Because once you realize how much is happening down there, the next question becomes unavoidable. Why this place? Endeavour isn't important just because it's active. It matters because it's one of the few places where that activity can actually be studied properly and over time.
Well, basically, it's close by. It's in our it's within our EEZ, our exclusive economic zone. We can get to it, and so it was made into a marine protected area. Quite, in the 2000 or so.
Protection comes first, because without it, you don't get reference systems. You get damage reports. And there's another reason why this place matters. One that's very practical.
First of all, it's a spreading center of a small plate, the Juan de Fuca plate, that is subducting under the North American plate. So you have a full plate structure that you can actually look at. This is the stuff that's being pushed out, and that's eventually going underneath the North American plate, and that's a system. And the fact that it is 300 kilometers off our coast is why we can cable it. So when, hydrothermal vents, let's say the mid-Atlantic ridge, you have to go a great distance, and there's always going to be, you can't really cable that kind of stuff. So this is right there, is connected very close to a highly important area for subduction, earthquakes and tsunami-genic earthquakes. So it really covers a lot of bases, and it's near enough to be able to visit often. It has a number of universities that have been doing it, University of Washington, UBC, University of Victoria. So it has that cachet.
And timing matters. Endeavour wasn't discovered yesterday, but wasn't discovered too late either.
Endeavour's only discovered in 1984, so this is a very new kind of thing happened. That we didn't know about before that. It was postulated, speculated, but we actually didn't. The first vent, I can't remember, early 80s, Endeavour 84. They finally actually got Alvin down there and saw, there's a whole bunch of stuff and there's a whole bunch of life associated with it.
That early start made a difference. It gave scientists time to understand the system before deciding how to treat it.
If you think about trying to study a volcano on land, let's say, you wouldn't do it by going there once every few years looking only 5 meters in front of you at any one time and going down and maybe having 4 hours to study the volcano, and then you come back in 3 years' time. So actually being able to do things in real time, I can look up right now, what's the change in the temperature of the vents? How has that changed in the last 24 hours? How has it changed in the last week? I can look at the camera footage and say, oh, look, that microbial mat that was growing like that has been eaten by something because it's got much smaller, or it's shed into the water column. And those are the kinds of things you can never do if you're just going out intermittently collecting one-off data. So, we've got some really unique instruments now too. So we can, for example, sample that black smoker fluid, 350 degrees C fluid, on demand from just through the internet. So if something happens, if there's an earthquake, we know there's been an earthquake because we've got the seismometers that are cabled. They tell us, oh, the ground just started shaking. Okay. Oh, yeah, this is a big earthquake compared to normal. Let's sample the fluid coming out the vent and see if that changed at the same time.
The more interesting thing about it is the fact, even though these are localized into certain areas, like the Endeavour segment sits, 300 kilometers offshore, and the next section is well down the ridge where there's other, there's interconnectivity between the ridges. So they're showing that there's certain, why are the same creatures living at Endeavour that are living somewhere else if they're not isolated? Because the ocean itself, as Lawrence was saying, basically it's interconnected along really long time scales. So basically the oxygenated water is ventilated in the Arctic and the Antarctic, and it sinks down. It gets cold, sinks down, and it ends up at Endeavour in 1,000 years. It's about 1,000-year cycle. So it's going to go. It's all connected somehow. Generally, when it's in the ocean, you're stuck with mixing processes that slow down the vertical travel times, and that's why you can pick up these signals at the depth of a vent, many hundreds of kilometers away from the actual vent site, because it's not going to go up and down. But it has no problem going side to side. It's once it's got its neutral density, that's where it goes. And these currents that we don't fully understand.
So Endeavour matters not just because it's spectacular. It matters because it's one of the few places where we can watch the planet doing its work, continuously and without interference. And once you start paying attention at that scale, one thing becomes clear. This system isn't quiet, it's alive. If Endeavour were just rocks and chemistry, it would already be impressive. But it's more than that. It's a system where geology, chemistry, and life are constantly talking to each other.
Sure. So, we trace it mainly by collecting samples, fluid samples from the ocean. And so you go out on a ship and you lower what's called a CTD rosette, an instrument that allows us to collect water samples. And then we bring them back to the lab and you analyze the composition of them, and you can see key element and isotope tracers that tell you that fluid has interacted with those hydrothermal fluids. And it's always at the same depth as the ridge. So it's about 2 kilometers depth in the Pacific. Right across the Pacific, there's a region. And it's enriched in elements like iron. So that's the iron that's coming out of the hydrothermal vents. It's building the chimneys. But it's also been spread right across the Pacific. And people are really excited about that because iron's a limiting micronutrient in the ocean and parts of the ocean. So everything needs it for primary productivity. And so knowing we have this source of iron into the deep Pacific is really interesting to biological oceanographers as well as geologists like me. Yeah.
What comes out these vents doesn't vanish, it moves. And it carries the signature of the Earth across the ocean.
To me, one of the most amazing things is, you have this hot fluid that comes out and it's chemically different to the surrounding fluid. But you might just think, okay, and then it mixes into the ocean and then it's gone. But you can actually trace that fluid geochemically right across for thousands of kilometers across the ocean. You can track that fluid. So to the other side of the Pacific, it still has a different composition. It's impacting the environment. There are particles, that black smoke. It's not smoke, it's particles that give it that black color. And those particles can be traced right across to the other side of the Pacific. So to me, that's amazing that, these vents are impacting the entire ocean in that way. So that's something I find fascinating that isn't generally thought about by people who look at them.
And this chemistry isn't subtle.
It's a big iron reactor down there. you put a piece of galvanized steel that you paint, let's say, you paint it red or something like that, and you got it sitting on you go back next year or maybe the year after, all is there is the paint. You just touch it and then the whole thing crumbles. All the iron is now this powder. So it's this red powder everywhere. So these things, they become very clear. Everybody knows, but it wasn't really predicted. I mean, it should have been predicted, but it's more of an experience thing. So you want to be able to have this, long-term kind of knowledge. So now there's no engineer at our engineering area that knows that we were not going to put in, stainless steel anywhere near the ocean, basically. Our first platform we put designed, we still have the same design, was made out of stainless steel, and we put it in Saanich Inlet, which is anoxic at a certain level. And it 6 months later, we pulled it back up, and whenever we had the stickers on, this is like you're trying to sell your operation. So you go down with ROV, take pictures of this thing. Wherever the stickers were, it was all the fact that you had another sticker on there lowered the oxygen levels so that stainless steel was eaten away underneath it. And then we can't use stainless steel. But we generally don't put things, the people who designed it were ROV pilots, and stainless steel and aluminum that works great for ROVs because it goes in the water, you clean it off when it comes back up, and it's fine. But if you put something in there for a year or 6 months, it can't work. So there's some engineering involved in there, but ahead of time. But often it's you'll say don't do that. That's not a good idea. And of course, there's lots of MacGyvering that goes on on the ship to figure out how to do things. I mean, that's the big thing, is to be able to adapt right away as we are there, because that's nothing that focuses you. You're out there. I can't remember what the numbers are. A dollar. A dollar a second, whatever is. That's you realize you got to get all this done, or you're not going to get funded to do it again, because you're just going out there, and it's hard to explain to people that it's a really difficult thing to do too. So you want to have success.
No sunlight, no photosynthesis, just chemistry turned into life.
It's hard to, compare biodiversity as for terrestrial biodiversity. The whole ecology there is based on a totally different function. Basically, it's chemosynthetic based. So basically, it's the bottom layer, instead of being green plants, there is this sort of utilizing the chemicals that are coming out of the actual vent fluids to make a ecological system. So the diversity is different. Like, it's totally different. It's nothing at all like what we have on. It's a geologic area. It's interesting. It's beautiful to look at. There's ecology there, but it's basically a passage from the crust into the ocean, and as previous statements by Lawrence, that affects at that level all across the Pacific. So this is hugely formative to the ocean environment.
Yeah, you can certainly trace that there are different things live at different vents, and how interconnected the species are depend on how long it is since there was a straightforward geological pathway between one set of vents and the next. So, for example, if the tectonics changes so that one ridge gets separated from another ridge, and there's not a direct transport for larvae between them, then they start to evolve separately. So kind of like the islands that Darwin looked at the finches with different features on.
Even here, geography shapes evolution. This isn't chaos, it's ecology.
You have microbes in there. You have a new vent shows up. It spits out a whole bunch of microbial stuff, and that's the basis of the basically food chain. We've gone to eruptions that just occurred with a rapid response, and basically as soon as we got there, which is a month, after things happened, these newer places were occupied by life forms. Yeah, we don't often appreciate the fact that there could be, similar amounts of species that live in the crust that we have on the actual planet itself. And they have a geological role. They actually change. They grab a bit of this mineral and that mineral and get energy out of it and make a third, mineral like serpentine or something.
No sunlight, no photosynthesis, just chemistry turned into life. And once you realize that, Endeavour stops being just a vent field. It becomes a living system and a machine of evolution even Darwin would be jealous of. And this is why scientists keep coming back to Endeavour, not because it's extreme, but because it forces us to rethink how the planet works. And once you accept this system is alive, dynamic, and connected, the next challenge becomes obvious. How do you actually watch something like this as it changes? If you want to understand a system like this, you can't just visit it once. You have to stay. So far, we've talked about systems, chemistry, life, but now let's talk about being there.
You'd board a ship and with an ROV and the crew, and then you'd head out just over a day's steaming to get to Endeavour. When you get there, then you locate yourself and then, you drop the ROV into the water. So using the A-frame on the back of the ship, and it takes, some hours to get down to the bottom. And then you'd have a van, basically, like a shipping container with typically a whole wall of TV screens looking at all the different cameras that the ROV is projecting back. And you have the pilots for the ROV who are really skilled at manipulating both the arms on the ROV and finding where you want to go. And, that's a big challenge, is tracking where you are and where you want to go. And then, you'd have typically 1 to 3 scientists in there or engineers telling the pilots of the ROV what they want to do, where to go next, what the aims are. Navigation's a big thing down there, so...
Let's go with this then.
All right, here we go. Going down. And can you tilt your camera up to see me better, or is it already tilted up? Bring your head around too. Your delta's getting a little high.
Yeah, maybe we want to pull out a bit.
2 kilometers of water, and then the seafloor.
The first time we laid the cable, going in there, and you've got that 5 meter kind of area where you've got really high intensity lights, but you can't see any farther. And so you're coming along, bumbling along there with a clear view of something very close up, and suddenly you walk right into the ROV flies into this field of these massive pillars, and you're going, wow, and they just come into view fairly quickly, and you're just, it raises, goosebumps on the back of your neck, right? It's so that whole thing, and then accidentally finding another one. Oh, this guy's here, and again, because of the viewing, you can't really see that far. You don't get a picture of the whole story, so you're completely lost in this little maze.
No horizon, no landmarks, just light and not much. It's darkness beyond 5 meters.
I always use 5 meters. It's, an R cube kind of, it drops down really quickly. But yeah, it's not far. It's just slightly bigger than the actual ROV itself. They got more lights now. You can look in the back. Often we use a 2-body system where it has a clump weight, but it has some control. It has some lights on it. And then you have your ROV. So that'll be above you. You'll be able to see the lights from a great distance, more than 5 meters. So, but all you see is a bunch of lights down there. And then you might be able to see what that light of the ROV is actually doing. So that's pretty fascinating. That's like Titanic stuff. They have to reconstruct the whole thing in a number of photogrammetric techniques to show you all of them, because you only see this one. Oh, there's the front end of the Titanic. And that's the same thing we're having in there. It's where we got this guy here, that guy there, and then you have to piece that together in your head and try to make the picture.
You never see the whole system. You assemble it piece by piece. And sometimes the pieces don't fit until you crack them open.
Sometimes a piece of a vent will fall off and break, and they grow all these, they're like geoids, where there's all a bunch of crystals growing on the inside, and it come from an area where it looks like it's completely like a muddy, not that interesting thing, and you crack it open, and it's this unbelievable, it's full of, lots of feldspar down, lots of really shiny things that it's so dark in the background and your lights are so strong. It's a fascinating kind of thing. There's a contrast thing that occurs.
Down here, appearances are misleading. And luckily, we have ROVs, which make the job way easier than going there in a submersible.
I can tell you, having been in one of them, you have even less view from there. So, I mean, at least with the ROVs, you have multiple cameras pointing in different directions with slightly different perspectives on them. In a submersible that I was in, you have one 6-inch wide window that you look through, and you look through that and nothing else for the whole time. So you really, you're not seeing a huge amount, So I think the ROVs are actually a far better way to do this than the human operated.
Even with today's technology, our maps fade at the edges, and beyond them, it's still dark.
And so that's one of the big research things that we're doing, is trying to put together an actual map of the area, because it's not, and this is a hard thing for a lot of the cartography people or GIS people, is that they don't realize it's the third dimension is just as important as the X and Y dimensions. In this case, it's just as vertical as it is horizontal.
Interesting enough, it's a very hard place to map because the mapping of the seafloor is generally done by using acoustic signals through the seafloor to the ships. But if you have a hydrothermal venting system that's spewing a lot of warm water, different water with different acoustic properties, it's very hard to use those ultra-short baseline systems to actually get the locations properly. So it's always off by 20, 30 meters. The maps are a little bit wonky down there. So it's sort of like, like trying to understand what's on Jupiter, like they like to say. You have a distance thing. And in this case, it's not actually in kilometers. It's because it's gone through this medium, the water, that is not as well understood, or maybe not understood, but it's a bad thing to propagate. You can't propagate radio electromagnetic waves, so you can't locate things that way. You need to use slow-traveling acoustic waves, and they get distorted.
Yep, even maps struggled on here. And that's where the science really starts.
So it's not, and that is based on, a number of predetermined dive plans that we make up. So this is exactly what we're going to do. We're going to replace this. We're going to move this over there. We're going to do this. We're going to sample this thing here to characterize that. So it's quite structured. It can be, because science is always good that way. Research, you basically want to be able to change anything in the last minute, because suddenly you see something unbelievable. Certainly you're not going to not look at it. And that's because, we have to now, plug this thing over here. No, our funding is based on basically operating and maintaining a observatory at Endeavour and all through the Northeast Pacific.
Yeah, Endeavour. The place where maps start to feel optimistic. Down here, nothing ever goes exactly as planned. Cable fails, tools misbehave. Sometimes you have to improvise fast. You adapt, you troubleshoot, you keep going. And that's where exploration really begins. No tiny window, no heroic solo descent, just teamwork, screens, patience, and the thrill of chasing new discoveries. Working at the edge of the map. Searching in the dark, never quite sure what the next moment will reveal.
You can see that these giant sulfide towers that are formed by the precipitation of minerals from these hydrothermal vent systems create a real navigational challenge on the seafloor.
You want to come up
and temperatures right at that vent, for those of you guys tuning in, can reach 600 degrees Fahrenheit, so it's very hot.
As it comes into contact with the cold seawater, the mineral load carried dissolved or partly dissolved in those fluids is very rapidly precipitated. And those minerals have a very dark color, black color, primarily iron sulfide with perhaps some copper and zinc sulfide in there.
For Steve and Lawrence, this must feel like a real epic adventure. And that's really cool, because let's be honest, who doesn't want to be Indiana Jones? And once you've figured out how to get there and how to see, the question changes and becomes, what happens when you stop visiting and start watching.
There you go.
Grip lock is on. Okay, so let's see what
There you
happens
go.
here.
I feel like I'm actually warming up physically.
Yeah,
Like, I'm
I just take our jackets off
like
here.
sweating.
We got 324.1.
Oh,
Will it
man.
get any higher?
Oh,
324.2.
3
3.
hit 321.
Oh!
326.
I can't believe it. Can you believe it, folks? I can't believe it.
I can't believe what I have seen.
For a long time, deep sea science worked the same way. You went down, you took a snapshot, and then you left. Endeavour changed that. Not because of a cable, but because we decided to stay.
That it's the one ridge segment that is a normal ridge segment that has all these instruments there deployed. So you can go onto the internet right now and look at the temperature of the black smoke event fluid coming out of a chimney, and that's being continually monitored. You can look at how many earthquakes have been in the last day. You can look at the video imagery of the animals living down there, so it's a location where there's so much information.
Time turns snapshots into stories.
So if something happens, if there's an earthquake, we know there's been an earthquake because we've got the seismometers that are cabled. They tell us, oh, the ground just started shaking. Okay. Oh, yeah, this is a big earthquake compared to normal. Let's sample the fluid coming out the vent and see if that changed at the same time.
Some of the most important processes don't announce themselves. They unfold.
But we really need to be able to build a community, and that's why, focusing on a cable that goes somewhere and attaches to one location tends to be, a way to be able to say, okay, we've got more than one measurements. It's not like you go out there and try to get all these different measurements on one cruise and say, oh, we should have figured out what was going on there. You have a steady sort of stream.
Staying doesn't just change what we see, it changes how science gets done.
I really think the future in a lot of science is to try to make it more multidisciplinary. It's very hard to do because if you know your science really well and you don't know other people's science very well, it's very hard to write papers where you get the right balance, where the physics isn't dumbed down to practically nothing. And you have to have this sort of dumbing down and raising. So when you get a peer-reviewed paper, whoever is reviewing it for the physics is saying, you're making it really too simple. It has to have, this is really not a very interesting thing. But the thing is trying to link physical phenomena with interesting geochemical phenomena, or more specifically, biological phenomena, which is easier to do, I find.
And when you stay long enough, no single discipline can hold the whole picture.
Yeah, there's a lot of collaboration. I mean, Steve and I have certainly been involved in a whole bunch of different studies together, published a bunch of papers on different aspects together. And yeah, lots of people collaborate. And those collaborations range from, detailed collaborations that lead to publications with multiple people who have collaborated, all being authors like Steve and I, through to much more helping each other, but without actually being involved in detail in the science. So, for example, the biologists might be going out there and not know where things have changed recently. So Steve's been out there recently, maybe, and can tell them, oh, go look at this area because things have changed a lot there. That area hasn't changed. So there's a lot of collaboration like that that's much more informal, as opposed to being co-workers on a publication or co-workers on a grant proposal and things like that. But yeah, I mean, it's hugely interdisciplinary. Everything we're doing, it involves people working right from the seismologists through the geologists, the fluid chemists, through to the biologists, the physical oceanographers. We all get together. We have workshops every few years where everyone gets together and catches up on what the latest is in every discipline. So there's a lot of feedback between things that way too. Yeah.
Some of the most important science never shows up in a paper.
You really need a lot of people working on this. There's just so much information flowing back from all these instruments, and it's such a complicated, interdisciplinary kind of topic, trying to understand right from the Earth producing the magma that drives the whole system, and that's starting 80 kilometers beneath the surface at 1300 degrees Celsius through to the microbes living in, 20 degrees C water that's percolating out at the surface and how that's impacting the overlying water column and broader oceanography. So you need people with all these different backgrounds.
Without memory, patterns disappear and mistakes repeat. Staying doesn't just add data, it changes who gets to see and who gets to understand.
And there's obviously some information gets passed on because it's been published or it's been written in after most cruises. There's cruise reports come out that document things in there. But there definitely is a loss to the community when someone's been working in an area, retires, and that corporate knowledge of these areas, and especially because they're so dynamic, like Steve was talking about earlier. Chimneys fall over, new chimneys grow. These things can grow at like a meter per year even. So you see a chimney and someone's saying, I think that's X chimney, and it's only if someone's been there multiple times that they can really say, no, that chimney wasn't there 3 years ago. Or that chimney, no, that's not that one because it used to be bigger, so it must have collapsed and a new one grown and stuff.
Without memory, patterns disappear and mistakes repeat.
Models aren't that concerned about the bottom of the ocean. The models are there basically to make sure that the atmospheric models are doing the right job, because that's the big reason. We want to know where we live, what the weather's going to be, not necessarily at the bottom of the ocean. So we often have a very confused view of what's happening in the deep sea. And that's a major area of scientific research that hopefully we're helping out by this observatory that we have there.
Staying doesn't just add data, it changes the questions.
Canada's a small country, so how many, I can count on one hand the scientists working at Endeavour. And we really have to rely on Americans. We have to rely on the French. We have to rely on, and then, the whims of those countries change. France wasn't going to support any kind of research in the Pacific because they wanted to concentrate on the Atlantic. So they do that, and now that's changing a little bit. So it moves around quite a bit. It's not. Canada sunk a bunch of money into making this happen. So we are, we try to corral Canadian scientists to go working at Endeavour, and of course American scientists as well. Basically, you build it, and then people will come.
Endeavour isn't important just because it's remote. It matters because we chose not to look away. Because beyond the edge of the map, understanding doesn't come from going farther. It comes from staying. And that might be the most important lesson this place has to offer.
Come out just a little bit.
Oh, that is incredible.
Did I tilt up too much? I don't know.
I'm pretty sure these are my favorite. This is my favorite sea creature right here.
Now, what does it use the eye for? Can they see down there? Follow bioluminescence or something?
Yeah.
Check that out.
Look at that guy.
That thing's cool.
Not have 100%.
I used to know what it was called, but I forget.
Okay, you can zoom, please.
The hunt for the name.
With pleasure.
You know how big its eyes are. That's how big he is. I'll try not to blind him now with my lasers.
Check me out. Check my back fins. Yeah, you like that back fin?
He's at least 10 centimeters.
This is my good side, right
He's
here.
At least 10 centimeters.
Yeah, there you go.
Check me out. Let me back up for you. Check out my nose. I'm hunting for the fish name. Oh, rough scale rat tail. I don't know.
No, it's not a rat tail.
Pacific flat nose. That looks more like it.
That might be it, yeah.
Hello, Pacific flat nose.
I'm going to name him Steve.
Thank you, Jake. Come on.
Absolutely. Bye, Steve.
Whoa.
Steve.
All right, gotta go.
See you later, Steve.
We've spent this episode deep below the surface, talking about vents, chemistry, life without sunlight, but Endeavour isn't just a deep sea story.
We're getting to the stage where we have more money. We have a lot of money for collecting data, or this is my personal opinion, and less money in relative sense to be able to work on all the data. So we're really, because, the higher level people think, oh, yeah, well, AI will come along and we'll be able to crunch these things down into nothing and we can just keep on collecting data. We really need to be able to build a community. And that's why, focusing on a cable that goes somewhere and attaches to one location tends to be, a way to be able to say, okay, we've got more than one measurements. It's not like you go out there and try to get all these different measurements on one cruise and say, oh, we should have figured out what was going on there. You have a steady sort of stream.
We're really good at collecting clues. What's harder is knowing which ones matter. And that's when a place like Endeavour stops being about data and starts feeling like a map, not for the ocean, but for bigger questions.
Just knowing about how these work on your own planet can give you ideas about what could be going on other planets. What are the key controls? What do you need? You need to have a heat source. You need to have hot rocks. It can't just be cold rocks, or else there's no drive for the rocks and the fluids to react with one another. And then there's other things like, okay, what pressure, temperature conditions are actually conducive to these systems working? How would they work differently if you didn't have salt in the water? The salt in seawater plays a huge role in how these systems work. So if we start thinking about what could be happening on Europa, for example, where people think there may be hydrothermal systems under the ice, well, how would that work? What do we need to know? So there's going to be a flyby mission that NASA are running in, I forget, 6 or 8 years or something. And a lot of the data that they're going to try to collect from these fluids that spurt up through the ice, those questions are driven by, okay, this is how we think those systems would work if they're working like Earth systems, and if the ocean on Europa is different, then these are the kinds of observations we'd need to look for. What organic molecules would we have to look for in there to tell us that the temperature or pressure of the hydrothermal system was different, for example? So, yeah, it's fascinating to think how these things could work on other planets. It's also very unconstrained, so it does allow you to have a lot of your imagination can come in as well as the science. But yeah.
So the only quickly answer the most interesting thing that people don't realize is that many planets, particularly moons of planets, are tidally sort of moved around because there's so many moons on, let's say Jupiter or Saturn, that they have a hot center, and they most likely have hydrothermal venting. That connected with the fact that it is highly likely that life started on Earth at hydrothermal vents. That means that opens the fact that there's this kind of heating of something and the expulsion of the mixture of having fluids on a planet and having solids on the planet. They have to interact and mix, and basically hydrothermal venting is one of those things that really drives that mixing. And of course, there's erosion and things like that drives the chemical balance of the oceans, but hydrothermal venting plays, again, a undetermined size of a role.
Endeavour isn't the answer. It's the clue that tells us where to look next.
We know more about the surface of Mars or the moon than we do about the bottom of the oceans.
And that should make us uncomfortable.
People don't really appreciate just the vastness, Like most of our planet is ocean. The bottom of the ocean is way more important to the planet than the continents. I think people also sometimes think that anything that happens at the bottom of the ocean doesn't really matter because it's out of sight and out of mind. And
that might be our biggest blind spot.
Yeah, if we take it, if we mine it and pull all that stuff out of there, how will that change the chemistry of the ocean? Because that's the big reason we're focusing on now is basically for mining. So they're going to mine it. If they mine it, that'll spread a whole bunch of that chemistry around in a much different way. And if we don't have the faintest idea what it'll do, it'll be similar to burning fossil fuels, where it was a good idea way back then, but the implications were kind of pretty planet ending.
Endeavour doesn't hand us answers. It gives us something rarer. The chance to stay long enough to see patterns form, to notice change, and to remember what the ocean usually hides. Eyes on Endeavour isn't about one place on the seafloor. It's about choosing where we keep our eyes, especially when the map fades, and the real work of the planet happens out of sight. As we close this episode, a great thank you to our two guests, Steve Mihaly and Lawrence Coogan, for taking us deep beneath the surface and showing us what it really means to observe, understand, and respect one of the most dynamic systems on our planet. Through their work at Endeavour, they remind us that the deep ocean is not distant or disconnected. It's alive, active, and deeply intertwined with the way the Earth functions as a whole, from chemistry and geology to life itself. Eyes on Endeavour is a story about curiosity, patience, and the power of long-term observation. Because sometimes the most important discoveries don't come with quick visits, but from staying, watching, and learning over time. This podcast is produced by Balad'EAU with the generous support of Ocean Networks Canada. ONC is one of Canada's major research facilities and is an initiative of the University of Victoria. It's primarily funded by the Canada Foundation for Innovation and by Fisheries and Oceans Canada. A special thank you goes to Tommy Goupil for editing and production, and to Andrew Lowen of the How to Protect the Ocean podcast. If you'd like to hear the full interviews with our guests, you can find them on Andrew's podcast. For this special series, each episode is offered in 2 versions: the full interview with Andrew and the narrative episode, more storytelling in style, here on Balad'EAU. If you enjoyed this deep dive, please subscribe, visit our website, and follow us on social media for updates. Your support helps us continue sharing these true stories of scientific discoveries, exploration, and human ingenuity. Thank you for listening, and until next time, keep exploring the oceans, paying attention to what lies beneath, and uncovering its secrets. I'm your host, Lyne Morissette. See you next time.